Welcome back to the course Modeling Combustion with Answers Fluent offered by Adult Systems. In today's class, we will discuss about non-premixed combustion model. So let's begin the class. So what is non-premixed combustion model? So this model is used to simulate non-premixed combustion flows where it is completely based on a conservative scalar approach. This is because all the thermochemistry is reduced to a single parameter, that is mixture fraction. So this mixture fraction is nothing but a local mass fraction of the burnt and unburnt fuel stream elements like carbon and hydrogen present in all the species like carbon dioxide, water, O2, etc. So when we are using this mixture fraction approach, there is no chemical source term present in the governing conservative equations which we defined earlier, that is the species equations, and so the problem simplifies to a simple mixing problem. Also in this model, probability density function, that is a lookup table, is used where the fluctuating mixture fraction can be completely defined. So we will get to know what is this PDF or the lookup table and how we calculate it and how we incorporate it in the simulation. So some of the key features of this model are, based on our problem, we can define 5 different state relations. It may be chemical equilibrium, it may be any flamelet model, etc. Also based on our problem, we can define what energy treatment the problem is dealing with, that is adiabatic or non-adiabatic. As I said about the mixture fraction, we can define as single mixture fraction problem or 2 mixture fraction problem where 2 fuel inlet streams are present. Next is the probability density function or the lookup table. Also in this model, like species transport, rigorous turbulence chemistry interaction has been taken care of. So some of the limitations of this model are that it cannot be used for compressible or non-turbulent flows, and also it is not applicable for pre-mixed systems. So now we'll see the steps involved in modeling non-premixed combustion model. So these are the complete 7 steps which we will go through detail one by one, and we'll understand how these steps help us in defining the non-premixed combustion model. So the first step, we will be defining the type of chemical description of the problem. After enabling the energy equation and the turbulence equation, we have to go into species, and then we have to enable non-premixed combustion model. Then we have to define the state relation and the energy treatment. So state relation out of the 5 and energy treatment out of the 2. Then we have to define if there is any secondary inlet stream. Also we can enable the rich flammability limit in this model, and we can also allow coal calculation. We also have to specify operating pressure for the system. So after defining all these terms, we will go to the second tab, that is the boundary tab. In this boundary tab, we have to define boundary species for the streams in the reacting system model. That is what fuel and what oxidizer will be in our system, and in what mole fraction or mass fraction it will be present, with what temperatures. We have to define all these things in this boundary. Next tab we will go, which will be the control parameters. So in this tab we can control what all species should take part and what all species should be excluded out of the system. Likewise, one example is that NOx species we can exclude from the equilibrium calculation using this control tab. So the next step is calculating the lookup table. So now everything has been defined, what all fuel oxidizer species and their mass fractions will be present. Now we will go and we will calculate the lookup table. So here automated grid refinement is one option which we have to enable. That is based on our mesh, it will take particular points and it will calculate the variance or the variation of the mixture fraction from one grid point to another grid point. This all process will happen behind, and we will get an output file, that is a PDF file, which we can export it and later we can import it during our calculation. One can also disable the automated grid refinement option, and then they can provide each and every term as it is present in the dialog box, and then they can calculate the lookup table. So the next step, defining boundary conditions. So earlier we have defined the mass fraction or the mole fraction in the boundary species. Now when we are defining for our surfaces the boundary conditions, then we have to define mean mixture fraction and mixture fraction variance. We have to specify this at our inlet boundaries, and it is very necessary to define because these are the 2 terms which will be calculated along with other governing equations. In some cases there will be diffusion problem also, so even that option is present in this model, then we can use inlet mixture fraction diffusion. So the next step is solution strategies for non-premixed combustion. So after defining everything, when we are about to start the simulation, it may happen that the solution won't converge and it may start diverging. This is because when we are dealing with the combustion calculation, there are large changes in temperature which will cause change in density, which in turn can cause instabilities in the flow solution. So there are various strategies one can follow, changing the under relaxation factors, mainly the under relaxation factors of density one can change. Even as a fluent sometimes recommend to change the value of default 1 to the maximum of 0.5. So the next and the last step, that is after finishing everything, the simulation is done, we can generate graphical plots or alphanumerical reports of the following terms. We can calculate or we can see through a 3D plot or graph of these following variables. So here I have added one picture which is showing 3D plot of a lookup table for temperature generated for a simple hydrocarbon system. So now we will see a demonstration of non-premixed combustion model with an example. So what all steps we have seen just now, we will apply all the steps one by one to model a non-premixed combustion problem. So let's begin. So in this video we will see how to model non-premixed combustion problem using non-premixed combustion model in ANSYS Fluent. I'm using ANSYS 2020 R1 here and I've already imported the mesh file here. Here we can see there are two inlets, that is two yellow color lines we can see. The first one which I am highlighting here with the mouse is the air inlet, and the second one, the smallest one, is fuel inlet, and the blue one will be used as an outlet. So this is the geometry we'll be using for non-premixed combustion model. As we have seen in the earlier classes that non-premixed combustion deals with two different streams from where air and fuel will be entered, and then with the help of mixing or an ignition source the mixture will be ignited. So for that purpose we need separate air inlet as well as fuel inlet. So this one will be used as an air inlet and this one will be used as an fuel inlet. So we will start modeling this using non-premixed combustion model. First important step is to check our mesh. So mesh check is done. Then we have to report our quality. So everything is done. Pressure based solver will be used and steady state simulation will be carried out. Next, going to models, we have to enable our energy equation. This is done. Viscous model, we are using SST K omega model. Next, coming into species, we have to enable now non-premixed combustion model. So in non-premixed combustion model, there are several options. For PDF option, we may include inlet diffusion or compressibility effects. As discussed, there are 5 state relations. So here are those. So we're going to use chemical equilibrium option here. There are other options also, as we discussed. For energy treatment we can use adiabatic or non-adiabatic based on our problem. Then we have stream options here, that is if you want to use any secondary stream other than these two streams, if you want to use any other stream which is providing entry of any mixed gases, we can use this option. Other than these options, we also have modeling settings, that is we can set the operating pressure over here in models itself. Then we can switch to fuel stream rich flammability limit, that is either we can go with 0.1 value which is the default or we can change it. Also we have coal calculator here. By using this option we can calculate the coal parameters. Then this thermodynamic database file name, this has nothing to do with our settings. This has already been taken by Fluent. So we will go into the boundary tab next. So this is the tab where we have to specify what amount of fuel and what amount of oxidizer is going in our simulation. So basically we have to define our species here, how we did in species transport model. Here we can specify the species in mass fraction as well as in mole fraction, but either we have to use any one option here. So I will use the mole fraction here. Here we can see in the oxidizer column, the O2 and N2 values are already fixed here. You can see that O2 will be entered in this much amount of moles and N2 will be entered in this much amount of moles. So we have to always remember and we have to take care of this, that oxidizer will be entering from air inlet. So the sum of the number of moles which is entering the air inlet, it should always be equal to 1, and same has to be applied for the fuel inlet. So what all species will be entering through fuel inlet, the sum of all the moles should be equal to 1. So now here we have to specify what fuel species we're going to use and what will be the contribution of their mole fractions here. We can also add some of the species using this boundary species option. We just have to type the chemical formula of the species you want to add. Then you can use this add option and then you have to specify the fuel mole fractions here. So right now for our simulation, we'll be using CH4, that is methane, as our fuel, and there will be some components of N2 as well included in the fuel stream. We can also add some of other species with the CH4, but here we'll be using your methane air combustion. So we will use mole fractions of fuel. So mole fractions I will be entering 0.90451. So for N2 it will be 0.09549. So this is the combination we are using for fuel and oxidizer. We have to take care that mole fraction of this CH4 and mole fraction of this N2 has to be equal to 1. Also it has to be equal to 1 for the oxidizer. So you have to be careful when we are importing mole fractions of fuel and mole fractions of oxidizer here. Then we have this temperature, so we can specify at what temperatures of fuel and at what temperatures of oxidizer the streams will be entering through our domain. So here our oxidizer will be entering, the air will be entering at 650 kelvins. So we have to specify this here, and we also have to specify this when we are giving boundary conditions. So we have to remember that our oxidizer, that is our air inlet from which the air will be entering, it will be entering at 650 kelvins. So then we have to go to control tab. Here we don't want to do anything. We have to keep it with default values. Then we have to go to table, and here we can see several parameters are being already imported. We just have to calculate the PDF table, and we have to make sure that automated grid refinement option has been enabled. So I will click on calculate PDF table. It will calculate. So we can see the progress in console. Okay, so after finishing we can see that PDF table successfully generated. Now we can check this PDF table as well. We'll just click on display PDF table. Here we can see that the plot variable is mean temperature. So we will go with the default values and we will click on display. So it will show us the PDF table which is calculated now. So we'll just check here. Here we can see this PDF table as I've shown earlier. It has calculated. Then we have to close this. And next we will do is we have to click apply. So the model will be applied. We have to just close it. So again here there are several options like inert, NOx, SOx, soot, etc. So based on our simulation we can use any of this. Then we will go into materials. In materials we can see that the PDF mixture has included all the species. So just go and click on the PDF mixture and we'll just check for the properties. Here for mixture, PDF mixture is there. So we can see that mixture species, then density. So density will be calculated according to the PDF table. Then specific heat mixing law. Then this thermal conductivity and other properties are there. We will go into fluid and we will see it for air. So here particularly for CH4 which we're gonna use as our fuel, we can check these all things. So specific heat we can change here. Then density also we can use some of the parameters here. Then there are some of these properties which we can change or which we can alter. So we will go with close. But right now we don't want to use any other properties. In cell zone conditions, it's just the fluid zone which we're gonna use. I'll just go and I'll display the geometry which we're gonna use. So display, close. Now we have to go into boundary conditions and we have to specify our boundaries here. So air inlet. So for air inlet we're gonna use as velocity inlet. So I will go and I will change some of the properties here. So velocity magnitude I'm taking 10 meter per seconds. So air will be entering at 10 meter per seconds. Then as discussed earlier, the air is entering at 650 Kelvin here. Then species, we don't have to specify any species here because this is air inlet. We will specify these properties at our fuel inlet. So we'll go with OK. And this fuel inlet, we have to specify it in mass. So it is mass flow inlet. In mass flow inlet, we have to specify our mass flow rate value. So this we don't want to use. I will use normal to boundary. Then this mass flow rate value I have calculated is 0.0625. Rest of properties will be same. Thermal it will be 300. Then species we have to be careful here. We have to specify our mean mixture fraction as 1. Then we have to specify mixture fraction variance as 0.25. Then I will go with OK. Then outlet, it is pressure outlet. Walls we don't have to change anything because it has automatically taken what we need. Then we just have to go into methods. Everything has been set. Just have to change it to second order upwind. We don't want to use any under relaxation factors here right now. We'll go and check for the equations. What all equations are there? So flow, turbulence, energy and PDF which we have enabled. We don't want any monitors as well. We'll directly go to initialization. We'll go for standard initialization and we want it to calculate from our air inlet. Then we have to select absolute. So we can check what all things are there. Is it everything correct? So everything is done. we have to initialize our solution. The solution has been initialized. We will go into run calculation and we have to specify number of iterations we want to solve. So I'll give 50 number of iterations, and main step, that is we have to write our case. Okay, so case is writing. So the case writing is done. Next important thing is we have to write the PDF as well, because sometimes if we want to do one more simulation with the same case setup, then we will need the PDF. So we have to write the PDF as we write our case file. So then we can go into run calculation and we can give calculate. So here we can see the solution has started. So the calculation has completed now. We will go for some post processing here. We'll go into graphics, go for contours. Then we will see, first we will check for the velocity. Velocity we will check, save display. So here for the velocity contour, we can see that how velocity is varying at this junction for air and fuel inlet, and the velocity maximum it has reached is 27 meter per second. So it has gone from 10 meter per second to 27 meter per second. Next we will check for the temperature. So temperature we have given 650 for inlet. We can see how temperature has gone from 299 to 1879 Kelvin. So we can see that the higher temperature has started from here, from where the fuel and air have combined together. So from here the air is entering, and so from here the fuel is entering. So the combustion has initiated at walls itself where they are intersecting at the first time. Then we can see a small little flame which is moving towards the outlet. This was done for just 50 iterations. If we have gone for more iterations, we could have seen a developed flame over all the domain. Next we can go for species as well. So we'll check for the mass fraction of CH4. So we can see how fuel is entered from this domain and how it has getting consumed from the domain from this junction as itself. And go for check for some products as well. We'll see for CO2. So CO2 we can see that this is the flame where air and fuel is getting consumed and where the products are getting started. So we can see that the combustion has started at these junction where the fuel which is entering from this side, air is entering from this side, and combustion has initiated. Next we will go and we will check some of the vectors so we can understand how this is happening here. We'll check for save display. So here we can see, so I will reduce this to 0.5 say. We'll check for save display. So it is reducing. So I'll reduce it little bit more. I'll go it to 0.4. We'll check for save display. So here it is little light. So we can see. So the air was entering like this here. Then when the fuel started entering here, we can see how they are moving towards this downward direction as where the combustion has initiated. Same here we can see that how it has reached the maximum velocity here, the blue color region which we can see. So the combustion has initiated here. So I'll close this and we will check path lines as well. So path lines we have to select any one parameter. So I will select velocity here and we need to select air inlet, fuel inlet. So we can see how it is coming from both the inlets. So I'll go for save display, and here as well we have to reduce the steps and path slip. So here for the settings of 500 steps and 1 path skip, we can see how it has gone. So we can see clear path lines here. So how the flow is varying, we can see clearly in this path lines. We can also pulse this. So we'll see how it is changing. So from air inlet and fuel inlet. So here they have merged together and the flow is moving towards outlet. So you can see a light blue color which has reached the maximum velocity here. So we'll stop this. We will check for other parameters. So the last parameter which we're going to check is XY plots. So for XY plot, I will select one parameter, that is we will check for velocity again, direction vector. We will check for air inlet plot. So here we have to change this axis option. So we will go for x equals to 0 and y equals to 1 because air inlet is present in transverse direction. So we will check for air inlet and we can see how velocity is maintained as 10 meter per second. For outlet we will check so we can compare both. We can see how velocity has changed from air inlet to outlet. Next we will check the same for temperature. So we'll go for temperature. So we can see there is a peak reaching at the middle where we have just seen how the flame is generated. So this is how temperature is varying. So we'll just check for fuel inlet as well. So for fuel inlet, we need to change this X value to 1 and Y value to 0 again, so we can check it properly. So we can see there is a peak at the end. Next we will check for species. So species we will check for mass fraction of CH4, and again we will check for our transverse direction. So I'll change these values and we will off this fuel inlet. So we can compare at our inlet and outlet. We can see how consumption of CH4 has begun. I'll close this window. Then we have not saved our data file, so we have to go into file, right, and we have to save our data. So we will save our data where we have saved our case file. Also in reports we can check our averaged value. We will go into surface integrals. We will go for mass weighted average, because when we are having any combustion problem we generally use mass weighted average. We will go for temperature. Air inlet we specified 650 Kelvin, is there. Fuel inlet we specified 299, this there. We have to check for outlet. We can see how temperature has reached 721 Kelvin. Also we can check values for temperature in between by constructing lines using new surface option. So this was all about non-premixed combustion model in ANSYS Fluent. We have discussed step-by-step procedure how we can use this model for a combustion problem which have two inlet streams. So the summary for today's class, we have seen that the non-premixed model is completely based on conservative scalar approach, because under some assumptions, the thermochemistry is reduced to a single parameter, that is mixture fraction. This model gives 5 chemical states and 2 energy treatments based on other type of the problem. Next, we can calculate the lookup table before the simulation, and then we can incorporate this PDF table or the lookup table in the chemical species calculations once we start the simulation. Next, we have seen that there are some limitations for this model, that it cannot be used for compressible or non-turbulent flows. Lastly, we have seen steps involved in modeling non-premixed combustion model for reacting combustible flows using a demo example. The references for today's class are following. In next class, we will start with premixed combustion model. Thank you.